look at methyl cyclohexane, again, as I ring flip, and ring flipping here is relatively fast, as I go from putting that methyl in the axial position versus putting it in an equatorial position, I can see there's actually a relatively decent-sized difference in energy between these two conformers. So how should I think about that difference in energy? We usually think about this in terms of what we call 1,3 diaxial interactions. So two hydrogens in axial positions don't bump into each other that much. Again, that's essentially a gauche interaction. But here, this hydrogen is kind of too close to this axial methyl group, and so there is a interaction there that two of them together give us about 1.7 kilocalories. Another way to think about this is actually using Newman projections. So again, if I employ the creepy eye kind of looking down the pipe here, I can think of this as two Newman projections with CH2s between them. And notice that here, this is a gauche interaction, just like we saw before. Whereas over here, putting that CH3 in an equatorial position, I don't have that extra gauche interaction. There's actually the two gauche interactions here, right? Counting this one and counting this H over here. Again, the two 1,3 diaxial interactions. If you remember back, each gauche interaction in butane was about 0.8, 0.9 kilocalories per mole. And so here, it looks like the math works out pretty easily. Two gauche interactions gives us about 1.7 kilocalories per mole. So the main point here is that whenever possible, I want to have my substituents in an equatorial position. That's going to be a lower potential energy thing. So if I have some substituted cyclohexane and ask, is the substituent usually going to be axial or equatorial, the substituent's usually going to be in the equatorial position. That's lower in energy because it doesn't have these 1,3 diaxial interactions, which is just another name for a gauche interaction. So what does that 1.7 kilocalories per mole translate into? For methyl's case, what it translates into is that at room temperature, we can expect a 19:1 ratio of molecules with the methyl in the equatorial position to methyls in the axial position, about 19:1. Okay, so here are some other substituents. Try to predict what order these would be. Which of them is going to be the greatest preference for equatorial position, and see if you can rank them. So you might think that it's just going to go by molecular weight. The heavier the thing is, the more it wants to be in that equatorial position. That's not quite right. So as you can see, iodine only has about a 70% preference for the equatorial position, which is much less than even ethyl. If I want to lock something into shape, a lot of times I'll use that terp-butyl group or something big and bulky like it so that it really, really has to be equatorial. But again, bulkiness isn't just molecular weight. Bulkiness is sort of branching because that branching is what causes the electron-electron repulsion and the 1,3 diaxial interactions that we talked about earlier. So the more branched the substituent is, the greater preference it's going to have for the equatorial position. Okay, here are two different di-substituted cyclohexanes. So for each of these, draw them in two different chair conformations, and then pick which of them is going to be the lowest in potential energy. Let's start with this one. So first I'm going to draw my chair skeleton. Okay, which one do I put this methyl on? Do I have to put it on this one? No, it doesn't matter. I just need to put it up. Wedge, we'll call the wedge up. So put it up somewhere in here. So sure, I'll put it here. Why not? Up. That means that there's an H going down there. Cool. Up an axial, down an equatorial in this case. So if I put that there, then I have to count 1, 2 carbons down. I have another up. So 1, 2, up. So let's try it another way. Notice I don't need to kind of draw it slanting one way or the other. I can just start at a different carbon. So if I want to go up an equatorial, well, I just put it here. That's up an equatorial. I can count 1, 2 away. 1, 2, 1, 2. and I need another up. Okay, so again, these are interconverting with each other. Which of these is lower in potential energy? Well, this one is a lot lower in potential energy because here I've got a pretty big 1,3 diaxial interaction between these two methyl groups, not to mention interactions even with this hydrogen and both methyl groups. This is going to be quite a bit higher in energy, and as a result, if you do the math, this turns out to be 99.8% in the di-equatorial conformer. Again, I want to put groups as far away from each other as possible, but to avoid these 1,3 diaxial interactions. Let's try this one. Again, I'm going to put my chair in first, methyl group up, so I guess I'll do it the same way I did last time. This will be up there, this will be up there. So here I've got a tert-butyl group. It is 1, 2, 3 carbons down the line, so 1, 4, 1, 2, 3, 4. And that's also up. So 1, 2, 3, 4. Here, up is equatorial. And here, 1, 2, 3, 4. Here, up is axial. Again, these are interconverting. And so which of these is going to be the most stable? So this is a little bit trickier because unlike in this case, I'm stuck having one of these two things be in an axial position. I can't have something be all equatorial like X right here. And so which of these substituents would rather be in the equatorial position? Well, my 1,3 diaxial interactions here are not going to be as bad as the 1,3 diaxial interactions between this giant tert-butyl group and the hydrogens next to it. Remember, the tert-butyl group, very, very bulky, always has an extra methyl pointing back in to these hydrogens across the ring. So this is going to be a really, really big effect. And so even though this does have some 1,3 diaxial interactions, this is still going to be the preferred conformer because it puts the bigger group in the equatorial position. So here we have two isomers, what we'll call stereoisomers next week, transdecalin and cisdecalin. So here we can because they are just cyclohexanes that are kind of fused together, we can still think in terms of ring flipping. One of these can ring flip easily. One of them cannot ring flip at all. So which is it? Well, let's try to draw these in two different ring conformations. So here's the difference. If I look at cisdecalin, I can still ring flip there. So here I've got these two hydrogens, let's say both up. So this is up in equatorial. This little H prime is up in axial. If I ring flip those, they simply change places, and I can still draw that. So cisdecalins can ring flip, but transdecalins cannot. So here is what transdecalin looks like. Notice I've got my hydrogens pointing in opposite directions. I would say these are trans to each other, and they are both axial. But if I put those hydrogens in an equatorial position, and I think about how I would close that ring, it doesn't fit, right? This one starts heading north, and once I get 4 carbons, how am I supposed to get all the way south here? It's just not big enough, right? So there's no way I can close that 6-membered ring. I just don't have enough room. And so I only see this. From a biological perspective, is it better to be able to ring flip or to not ring flip? Well, obviously it's going to depend on the context. But a lot of times, as I said, biochemistry depends on structure. Something structure gives it its function. And so many times we want something to have a relatively rigid structure, not one that's floppy and I need to wait for it to eventually get the right shape to do the job. Transdecalin and molecules like it are stuck in this shape, more or less. Yeah, it can wiggle on the ends, but for the most part, it's a relatively rigid molecule. And so we see lots of biological molecules kind of based off of this shape. For instance, this is cholesterol, the most common steroid in the body. So steroids often have this 6-6-6-5 tetracycle shape, and they very often have that kind of transdecalin-like link between two six-membered rings. Right? You can also see there's a trans linkage here that's going to make this 6-5 ring system less flexible. In lots of chemistry, but particularly in biochemistry, shape dictates function. And transdecalin has a more constrained shape, which might give us might be important for its function overall.